Hi there. My name is Chris Johannsen. I'm a PhD student at Iowa State University studying computer science, and today I'm going to be giving a talk on how C2PO translates for R2U2 and how we make specification more practical. So to kind of set the stage in terms of the sort of context that we're talking about here, we're going to be talking about runtime verification. It is a technique for checking that a system behaves according to its specifications at runtime. So an entity or something that does runtime verification, that performs runtime verification, is going to take two inputs and give one output. It's going to take in, number one, it's going to take in its specification that you're looking to monitor. And number two, it's going to take in the actual system data. And then it's going to output verdicts. So that is, it's going to output whether or not true if the data matches the specification and false otherwise. Um, so a little bit more deeply into sort of some of the context that we're talking about here. So the NASA Lunar Gateway Vehicle System Manager is a team that elected to use the responsive, realizable, unobtrusive unit for performing runtime verification on their system. Some of the reasons why they chose R2U2 over other entities that perform runtime verification is that R2U2 can actually run in real time, so it can take in real system data and give you real-time verdicts as to whether or not your specifications are being upheld. It's flight certifiable, so it has bounds, hard bounds on its memory, and hard bounds on some of its time and computation time, and that it interfaces with NASA Core Flight System or Core Flight Executive well and easily. So it's easy to use in their operating systems. So here's kind of a high-level overview of how R2U2 interfaces with the NASA Lunar Gateway VSM in particular, and it might give a good idea of where R2U2 fits in systems in general and what it does, right? So we have this system where you have a bunch of like computer applications, N of them say, and then R2U2 kind of sits like one of them. It sits on the communication bus just as any other flight computer app would. It takes in real-time data from that communication bus, and then typically, at the mission start time, and you can do that. You would give R2U2 your set of specifications that you're looking to actually monitor. Importantly, R2U2 is cool that you can actually flip those out. You can swap them out if during system execution you realize, oh shoot, we want to monitor this specification instead. You can actually swap it out for another one, and you don't need to recompile R2U2 at all, right? R2U2 stays the same. It's just the specification that changes, just the input, right? And then, importantly, R2U2 outputs verdicts and sends those out on the communication bus. So any flight computer app that might be, interested in knowing whether or not a certain specification is being upheld can determine whether or not that's true. So for instance, there you might have a specification that tells you whether or not flight computer app 1 is behaving properly, and you might use data from computer app 1, 2, 3, and maybe a couple, directly from some sensors or whatnot, right? You can imagine something like that. And then R2U2 say takes that in, takes the specification, takes the data in, and then determines, hey, flight computer app 1 failed this specification. And you would send that off to the communication bus, and you could imagine how maybe flight computer app 2 depends on computer app 1 in some way, and in particular, that behavior according to that spec. And so it might read that verdict, to get that verdict, and say, "Hey, okay, this is good to know. Like I shouldn't continue with normal functioning. I should go ahead and do something about this. The system has degraded in some way, and I can go ahead and do things. And the important thing about this is that R2U2 does this, as opposed to writing your own monitor that can monitor real hard faults, maybe local to each computer app. R2U2 can monitor things at a system level, so it can kind of aggregate a bunch of data for you and then, reason about that data at a very high level as opposed to at nitty-gritty inside each application. And you can also do things, that are timing wise, you can talk about things more easily. And we'll kind of get into that a little bit in a little bit here. So I want to focus in a little bit on that R2U2 specification. So what R2U2 takes as an input there, as opposed to the data or verdicts, we're going to focus on what those specs are, what R2U2 takes as input. So in particular, R2U2 specifications use a logic called mission time linear temporal logic, MLTL. You can think about this as basically just Boolean logic plus the ability to reason about and talk about time. So you have basic Boolean variables, so you can talk about A and B being true. But also you can talk about things like A being true from time steps 0 to 5, or, say you make a time step is like milliseconds, right? You'd say that I want A to be true 0 to 200 milliseconds from now. You can reason about things like that. And so, you know, we'll kind of look at an example of what this looks like. So this formula here is maybe an MLTL formula. So we have 3 Boolean variables here, A0, A1, A2, A3, and we could say things like A0 implies A1 and A2, or, and then this is an eventually operator. So this says this F053 says that A3 is true 0 to 5 time steps from now. So from 0 to 5 time steps from now, we'll go ahead and it's only true if A3 is true within there. Importantly, what a time step is, R2U2 can be run asynchronously. So you can basically manually, you can hook it up to a clock and have it, synchronously. Every time step is a consistent time, so you can make a time step correspond to a second or a millisecond or whatever, right? Or you can make it run asynchronously, and you can tell R2U2 to do a times, to iterate in time, whenever some event happens, right? It can be event driven. So that's kind of an important note here, what a time step is. Typically, we think of it in terms of a unit of time, but it doesn't have to be. So just kind of getting into the nitty-gritty a little bit of R2U2 and its implementation, this assembly is what R2U2 actually runs. This is what it reads and what it executes in order to determine whether this formula here is true. So importantly, R2U2 doesn't use variable names in its assembly file, so you need to encode everything as the A0, A1, A2. I use this in the formula because it just is easy to read, but importantly, R2U2 doesn't support variable names here. I need to load it directly from a signals vector, essentially, or an atomics vector that corresponds to, and the A0 here would be the index in that vector. And so we load in our system data, we perform the conjunction there, that and at N3, and that node 5 does a future of node 4 here, and the 0 to 5 are the arguments to that. And you can just sort of see how this assembly corresponds to this this formula here. So this is essentially just a representation of the abstract syntax tree of this expression. So as you can tell, this is pretty tough to use kind of as a human. It's kind of tough to write this manually. It would be tough to do this, especially for a real world spec. I mean, it's kind of tough to do this manually for this little spec here. You'd have to do a lot of work making sure that you're checking everything against example traces and whatnot, and making sure that everything matches up how you expect it to be. So just to kind of illustrate further, right? So here's just a sample of some real world specifications I pulled from this, A7E's aircraft software requirements document. It's kind of word vomit on this slide for a reason, because English high level requirements are a little, verbose sometimes, and they have a lot of words and they say a lot of things. It's very dense. And kind of getting the idea and imagining in your head, I kind of want to illustrate how, imagine how you would go about writing these specs directly in this assembly format here, right? So this first one, the IMS diminishing weight count shall be changing and the state changing once every 5 milliseconds, approximately 2 to 300 microseconds before changes of the IMS torque counters. So, an important thing here, right, is that we could, for instance, encode the IMS diminishing weight count state being changing as a Boolean, right? So that state can be changing or not changing, right? And then we could talk about, we could talk about it being there, having that occur once every 5 milliseconds. And then we can talk about detecting changes of the IMS torque counter or whatnot, right? But you can imagine, without using variable names, this is going to get arduous. And especially when you do a bunch of these, they're each individually going to be difficult, and they're going to be difficult to check. So just in particular, writing these manually from an English high-level requirements is time-consuming and, frankly, error-prone. You're bound to make a mistake, writing these, formalizing these in MLTL directly, and then further in R2U2's encoding of the assembly. So that's where C2PO comes in, which is the configuration compiler for property organization. I think it's a pretty apt name. Here in this right side, this is sort of a workflow. This picture here, this figure here is just a workflow of how one might use C2PO and R2U2 on their system. So the target system here, this dash box and these red boxes are the same as in this here, right? You can see the data and R2U2 specifications are inputs and the verdicts are outputs. So now, though, instead of directly writing our R2U2 specifications and writing them in an assembly format, we have this compiler, the C2PO, right? So now we can take our system requirements, which is this here, right? This is that first blue box, that system requirements box. We can translate that into a C2PO specification, which I will get into shortly. Hand that off to C2PO, which will then transform that properly into the R2U2 assembly or the R2U2 specifications for actual monitoring. So just to kind of give an overview in terms of what specifically I want to go over here in this talk, we have this new specification language that's, a very cool format and provides a standardized way of viewing things. And especially when you have many high-level English requirements and you want to format them all and store them in the same place, it makes it very easy to look at and for someone who's not familiar, come up to speed and understand what's going on. Um, and then we have some pretty cool features in this language in particular that supports some common specification patterns like assumed guarantee contracts, which the VSM team actively uses, for instance, and then some set-wise specifications. So talking about groups of things and groups of entities, and I'll get into that in a little bit here. So just to start off in terms of C2PO, so it's input language. This is designed from scratch. It's inspired from SMV, which is a model checker. If you're familiar with that, comments are preceded by 2 dashes as in SMV. And then we have 4 sort of sections to our input file. So the first section here, we can declare a C-like structs. So we can reason about and we can organize our data in a way, because oftentimes when we're talking about and specifying things, we're talking about something like a task or a request or something that has multiple things. A task might have a timestamp on when it began, when it ended, whether its state is active, is completed, is stale, or whatnot, right? You might have some things like that. And you might want to organize that in this sort of structure here. And then we have this input section. So this is where you declare all of your input types. So whether that be, these are the input your signals, right, from your system data. So importantly, we support R2U2 supports Boolean, integer, and float primitive types. And kind of a note here to make is probably a good place to note this is that R2U2, while works for software, can monitor software very well and effectively and efficiently as it does as it can for the Lunar Gateway team, right? Which is what we're targeting here. R2U2 also is implemented in hardware for FPGAs. And so, there's a bunch of sort of configurations you can make to R2U2. You can turn on and off certain features. So maybe you don't need the support for integers. Maybe you only monitor Boolean variables, right? Or there's certain sort of depending on your system constraints, you may not need integers or floating points, but we support them, right? They're optional. And then after that, after the input section, we have the define section, which you're allowed to define various macros. So in this case, the left-hand side equal the right-hand side. Anytime you see that left-hand side term, it'll just expand out to that right-hand side. So, and then finally, in our most important probably section here is the spec section, which is where we actually declare our specifications. So specifications can have labels. So, when R2U2 outputs whether a specification is true or false, it can print out or it can give the actual label with that instead of just a formula number, say, or a specification number. Taking a look at kind of how these structs are working, right? When we say T.A here, notice that big T we defined as a test XYZ. And because in the way that we defined the test struct, ABC is in that order. It's order sensitive here. So test of XYZ means that the input X wires up to member T.A, the input Y wires up to member T.B, and Z wires up to the member T.C. So here now, this T.A greater than T.B, that would just expand out to C2PO is just going to automatically reroute everything, and it's going to come out to be saying X is greater than Y, right? So that's just kind of how C2PO does it. And of course, we have this sort of temporal operator here that's eventually Z is equal to 2, which is all fine and well. So that's just a sample file. And you can kind of imagine how this can be used for various number of specifications, right? So let's just move on and talk about some other cool features. So in particular, we can talk about some assumed guarantee contract support and how we help support those directly. This is a paradigm that's used oftentimes when we're writing requirements. So I'd say it's good to talk about these, and maybe driven by an example is a good way to explain how we support assumed guarantee contracts or AGCs. So in this case, we take the assumption that task A is active, and we have a guarantee that task A shall be active for at least 3 seconds once it is active, right? So in C2PO, we might write something like this would be a sufficient monitor for looking at the specification and outputting proper verdicts. So we have the struct section. We want to declare a task. In our case, we're only really monitoring whether it's active or not. So we just have one member here. It's an active and it's a Boolean. Then we only have one task that we want to monitor, task A. So we go ahead and declare that. And then finally, we define task A as a task which takes in member A here, input A. And then finally, our spec section. We have an assumed guarantee contract. They have to be labeled. So this one has a labeled C1. And then the important syntax here, the syntactic way that we recognize whether it's an AGC, assumed guarantee contract, is that equals greater than sign. So the assumption is on the left-hand side and the guarantee is on the right-hand side, right? And this corresponds exactly to what you kind of would expect here. So the kind of important cool thing and how we actually use this is that, number one, you can write this in C2PO and kind of understand what's going on, and it's a cool way to organize these requirements, these formal specifications. But more than that, R2U2 will actually output whether C1 is true, false, or inactive. And that's very useful, especially when you're debugging these things and you're trying to understand, why the specification is behaving according to some data. It's very useful to see that, okay, this spec is true, but like, why is it true, right? Because these assumed guarantee contracts, they kind of, when they're evaluated, when you actually evaluate them, they're very similar to an implication, right? It's an if then else false, right? So if true, if the assumption is true and the guarantee is true, then it's true. If the assumption is false, then technically it evaluates to true, right? So, but that's actually a useful distinction to make in this case for assumed guarantee contracts. I want to know whether my contract is being upheld because the assumption is failing, because the assumption just isn't true, so I don't really care, right? In that case, it's inactive. And that's distinct from the case where both the assumption and guarantee are true. And of course, I care about the situation where they fail, where the assume holds and the guarantee fails. Of course, I care about that, and I'll report that. But for these purposes, it's useful to know that sort of tri-state stuff. So that's sort of how we support that, and especially when it comes to debugging and looking at, and analyzing our specifications and making sure that they're actually reflective of our system. So moving on from AGCs, we could talk about some set-wise specifications because, in this example, we only talked about one task, right? Task A. It's not likely that we're only really going to be talking about one task. In our system, we probably have many tasks that we want to monitor. We probably want this to be true for every task that shows up. So we'll move on from that example. And we'll talk about instead a system, a sort of request granting system you could think about, right? And so this sort of English requirement, this is sort of something you might see. It seems like a common pattern that might show up is that every request shall be granted within 5 seconds. Okay. At first glance, this seems like a pretty simple requirement, right? Like, okay, this seems easy enough. But how do we do this, right? And it's actually a little bit more complicated than at first glance, right? Because we don't necessarily, this requirement doesn't tell us which requests, right? It just says that every request. So if we try to encode this directly in MLTL as an MLTL formula here, right, that we would write in our C2PO spec section, well, this is a problem, right? Because while it totally corresponds to our requirement, right, I don't know what R is. It's very vague to me what R is in this requirement. So that just doesn't make sense. I can't do that. So importantly, kind of the next step from here and what we sort of suggest people do when you're talking about sets like this is you consult your system constraints. So in this case, and in almost any other case, in any system that has this, sort of request handling system, we'll ask the question of how many requests can the system handle at one time. So typically this might be, like a queue or a list or something, right? Where you're actively taking in requests and you're actively granting them in real time, right? And requests enter and leave enter and exit the list or whatever you have, right? For organizing that. But it's really important that this bound on how many requests you can handle exists. It really is important because if this bound doesn't exist, then it means one of two things. Either, first of all, you don't actually have the hard bound, in which case, say some other entity that's communicating with your system floods your system with requests, and then you're dynamically allocating stuff, and all of a sudden you've run out of memory. So that's a real problem. So first of all, you should have a bound on that. Or second of all, you actually do have a bound. You have a maximum number of requests you can handle at once, but you don't explicitly say it, in which case you're probably going to be dropping requests without knowing it. And that's also not a good thing, right? So we want to be able to, any system that has this should have hard bounds on these sets of things, right? You should know in either case. So the idea here is we can use this bound And then basically we can track sort of the active requests and monitor the formula and monitor that formula above, right? And so we can sort of like before we even deploy, we can sort of allocate all of the memory that we kind of need to monitor these sets, um, and then swap things in and out, allocate slots for monitoring these entities at once, right? So here's sort of an attempt at formalizing this in C2PO, right? So again, the requirement is every request shall be granted within 5 seconds. So first of all, we'll define what a request is. Um, we're going to have 2 Boolean flags. Of course, we're going to need to keep track of whether it's granted, but we're also going to keep track of whether the request is active. So we'll get into what that kind of means a little bit here. So, and then finally, let's assume for the sake of argument, right, for this example, that we have 3 requests. We have a maximum of 3 requests we can handle at once. So we'll go through the input section, right? Of course, we'll declare all those variables. And then in our define section, we'll declare the 3 requests and then declare a set that is composed of those 3 requests. Now, what are these requests here? It's important to know these aren't the actual requests, right? Like when I get a request at timestamp, 3, and then I get a request at timestamp 5, maybe I put the request at timestamp 3, I put that in slot 1. So I hook all that data up to A1 G1. And when the request at timestamp 3 gets granted, G1 is going to be true. And then at timestamp 5, I hook that request up to the one in slot 2, right? And so when that's get granted, G2 gets flipped to true. And then when the timestamp 3 request and slot 1 R1 goes away, the active flag goes false again. And then I can slide another request in, say at timestamp 8. I can slide that one into R1 again. And so we can kind of, keep track of members of this set of which requests are in our set at once with this Boolean flag active, right? And so kind of the important part here and sort of how we would actually specify this is we have this for each operator, which just expands out this right-hand clause here and just does a conjunction of it over all the elements in the set. So here we have for each little r in big R, little r dot active implies that eventually from 0 to 5, little r is granted. And you can see in that commented line above, this is just going to get translated and expanded out to R1 dot active implies eventually 0 to 5, G1 dot granted, and R2 dot active implies eventually from 0 to 5, G2 dot granted, and for R3 as well. So this is just kind of a cool way that we can go ahead and talk about set-wise things in a bounded way with memory guarantees and do them, guaranteed that we'll be able to do it in a reasonable and efficient manner. So just to kind of go over a summary of what we talked about today. So R2U2 is a runtime verification tool that can target systems that require, real-time performance, flight certifiability, or interface with, a variety of target systems. And then C2PO is our cool little compiler that makes writing specifications for R2U2 easier by providing support for things like standardized input structure, C-like structs, macros, assume guarantee contracts, and set-wise specifications. And I implore you to go ahead and consider using R2U2 for any of your real-time system needs, and hopefully using C2PO as well, or maybe using the C2PO feature set or input language for something else, another application. That'd be very cool. Feel free to reach out if you have any questions. And thank you for your time.